We're now going to cover case study ex47. This case study showcases Java StampedLock as well as other interesting Java object-oriented and functional programming features. In particular, we're going to show how a Java StampedLock synchronizer can be used in conjunction with a Java HashMap, not a concurrent HashMap, just a good old Java unsynchronized HashMap, in order to compute, cache, and retrieve large prime numbers. And we're going to show off a bunch of StampedLock features. We're going to show off pessimistic write and read locks. We're going to show the use of an optimistic read lock, and we're also going to show the use of something called a conditional write lock. So the ones that are pessimistic, it's kind of the locks are half empty. The optimistic ones, the locks are half full. And the conditional write locks can kind of morph themselves between different types of locks under different circumstances. We're also going to show how to apply a memoizer. Memoization is a technique that's used to optimize the execution of methods by caching their results. So you don't have to perform a long-running operation more than once. You can do it one time and then cache the results. We're also going to show how to apply the Java structured concurrency framework, which improves the implementation, readability, and maintainability of concurrent code by taking one task and splitting or dividing it up into subtasks, and then processing all those subtasks in parallel, and then joining all the results back together to create a final reduced result. And then finally, we're going to compare the performance of various thread-safe maps. We're going to show one that uses a synchronized hash map, and we're going to show one that uses a concurrent hash map, and we're going to show one that uses a StampedLock hash map implementation. And we're going to compare them across different properties when doing these computing, caching, and retrieving of large prime numbers. You can find this code in the ex47 project in the Java 8 folder in my live lessons GitHub repository. And so let's go ahead and take a look at that code. So here we are in the ex47 project. This is a fairly lengthy piece of code, so I'm going to probably break this up into a couple different pieces. We'll look at them in different parts. Let's start by taking a look at the ex47 class itself, which showcases and benchmarks the use of Java's object-oriented and functional programming features in the context of a so-called memoizer. This is the thing that caches the results. It's configured to either use a concurrent hash map, a Java collections synchronized map, and/or a hash map that's protected by a stamped lock. And we use this memoizer to compute, cache, and retrieve large prime numbers concurrently via Java's structured concurrency and virtual thread objects. This example also shows some other things like the use of the Java record data type and some advanced features of StampedLock. So let's start by taking a look at some of the ways we've defined this. We got a couple fields. We have one that keeps track of the number of items that are pending. That's just used for diagnostic purposes. We have a list of randomly generated large integer objects specifically set up to have duplicates so we can leverage our memoizer. And then we have a main entry point, which creates an instance of this class and then runs its run method. You can see the constructor parses any arguments that are passed in. We use this to give arguments to configure the way the program works. For example, we can give it the number of items we want it to process, the number of random integers. We can set the type of memoizer implementation for the stamped lock, and so on and so forth. We'll look at that later. And then we go ahead and we generate some random data of count, size, up to max value, which are parameters we can set. Here's generate random data. This just uses good old Java 7 and before features, the old school Java classic object-oriented features to make a new list of random integers, a new random number generator, and then we generate count random integers between max value minus count and max value. And we do this in order to try to ensure that we got duplicates here, and we put them in that random integers list, and then we return that random integers list. So that's where we get the data from. And we're going to have all the different strategies, the concurrent hash map, the synchronized map, the stamped lock hash map, and so on. They're all going to work on the same data, thereby allowing us to do apples to apples comparisons of their performance. Here is the run method that gets called back after we make the object that is the ex47 object. And what this does is it's going to create and time 3 memoizers. And we'll talk later about what a memoizer is. And we're going to configure the first memoizer with a synchronized hash map, which just has a single lock, which is obviously a point of contention and overhead. We're also going to make a memoizer that's configured with a concurrent hash map, which uses a lock per hash table bucket, much more scalable. And then finally, we're going to make ourselves a stamped lock hash map, which uses various features of stamped lock. And then we're going to make a memoizer that's configured with that particular type of hash map, the stamped lock hash map. And we'll look at all this code in more detail here shortly. But what you're going to see we're going to do is we're going to time each of these different implementations and see how long they take to run. And when we're all done, we're going to print the timing results, which will be sorted by fastest to slowest. And then we'll also print the results of the StampedLock HashMap manager just to see what's in it when it's all done. They're all going to have the same values, of course, but we're just picking one to print. So that's kind of where things start. What I'm going to do in the rest of this first video is show what the memoizer is. And then we'll stop and we'll do the next part of the video and we'll talk about some other parts. So let's go take a look at what memoizer is. So you can see memoizer comes here in the utils folder, and it defines what's known as a memoizing cache that synchronously maps a key to a value that's produced by a function argument that's passed to the constructor of this memoizer. If the value had been computed previously, it's returned rather than calling the function to compute it again. So it's basically caching it. The Java map compute if absent method is used to ensure only a single call to the function is run when a key and value are first added to the cache. And we're going to do some interesting things here. We're going to have some different implementations that we're going to use to pass in as the map argument. And so the map argument will determine what kind of map is used. So we're going to have the concurrent hash map, synchronized map, which is correct but inefficient, and then the StampedLock map, which is typically better than synchronized map, but not usually as scalable as concurrent hash map, as you'll see when we take a look at this code here later. So this is actually inspired by an example from Brian Getz's book called Java Concurrency in Practice. I just kind of blinged it out a little bit to make it more cool. One of the things I did was I have the memoizer implement function, so it can be used anywhere a function's expected, which is a nice way to be able to parameterize memoization transparently into your code. You can see here that we have a field called mcache, which is going to be the type of map we pass in, concurrent hash map, synchronized maps, the StampedLock hash map, and so on. And then it's going to have the function that produces a value based on the key. Both of these things are passed as parameters here, as you can see, and stashed away in the fields. And of course, they're private final variables. Down here, we have the apply method. Apply is the method that's going to be implementing the functional interface. Remember, we inherit from function, so that means we have an apply method, so we override that. And what that does is it simply forwards to the underlying map, passing in the key as well as the mapping function. And if the key is not already in the map, then that function will be called to compute the value, and that value will be stored under that key. If it is already in the map, it'll just return it. In any event, it's always going to do this atomically because of the types of maps that we use to configure the memoizer with. There's also a couple other methods here like remove, which removes the key, size, which returns the number of elements that are in the map. And then we have another method that returns the underlying map that's used as the cache. So that's what memoizer is. A very, very useful mechanism to have around. I used it a lot in my concurrent programs, and I think you'll find it very useful for things that you do as well. So we're going to stop there for this video, and then we'll continue on in part 2 in just a moment.